Bem-vindos to one more episode of the Type Theory for All podcast. As always, this is your host, Pedro Abreu, and today we have a long requested episode with Mario Carneiro. Mario has done his both master's and PhD at Carnegie Mellon University. He is the creator of Mathlib, of Lean4Lean, and of Metamath Zero. He's currently doing his postdoc at Chalmers University, particularly to work on CakeML. In this episode, we dive into his many projects, his views and foundations of theorem provers, their semantics, their properties, their interoperabilities, and the whole shebang. I had the great pleasure to actually record this episode in person at Chalmers University. It was an amazing conversation. He's such a great guy. I am sure that you guys will enjoy this episode as much as I did recording. But before that, real quick few messages for you. Here at Type Theory for All, we have a mission with open access and open education. We abhor the possibility of getting our content locked behind some kind of paywall. So in order to help us to deliver to you the best of type theory, programming languages, and formal methods for free, we humbly request your support through Ko-Fi. Simply go to our website, typetheoryforall.com, and follow the prompts. A donation of any amount, even $5, will be of a great assistance to our cause. Also, don't forget to follow us on Twitter at TT4All and joining our Discord. We're currently organizing a weekly study group to learn Cog through software foundations. So if you think that's something you'd be interested in, go to the website and join Discord today. For the first time in the life of this podcast, we are actually in person. And it's my great pleasure to be here with nobody less than Mario Carneiro. Welcome to the show, Mario.
Hi.
We are actually in Chalmers right now. You just started your position this week or last week?
Yes, last week. That's right.
How is your adaptation going, man?
It's been quite interesting. This is the first time I've ever really been outside of the US for an extended period. I was in Bonn for 3 months before this, and now I'm going to be here for 2 years. And it's a really new experience, and it's great being in Europe.
Who you're working with here?
So I'm working with Magnus Marin, and he does CakeML, which is a verified compiler.
Dude, you like to work with everything. Like you came from Metamath, Lean4Lean, Mathlib, and now CakeML. You just want to work on anything related to.
That's right. Yeah. So I mean, I have used to some extent Metamath, Mizar, Lean, Isabelle, Coq. I need to get more Agda experience, but this is a great place to get it.
I assume. So tell me. Okay, so how was your academic journey? How did you get involved into so many projects? Tell us a little bit about your story.
So I was an undergraduate at Ohio State University. I was studying physics and mathematics and computer science, and I was actually having difficulty finding sort of projects to do, but I found Metamath in sort of just random web search one day, and I was, reading a book on set theory at the time, and they were actually formalizing that book. And so it was very, very interesting. And especially when you look at like a set theory textbook, it'll have that sort of rigid structure to it. And it makes you feel like, if only someone had the idea of putting this in a computer. Yeah. And so it was really interesting to see that people were actually doing this. And so I was very impressed by the work, and, clicking around, there's some HTML pages. You can really see sort of how things link together. And so that was sort of my introduction to interactive proof systems and to formal verification in general. And so I was doing it as a sort of hobby. Eventually I graduated. I still wasn't really doing anything academically with the people at OSU. So I became like a Java programmer. And while I was doing that, I was sort of doing some proofs on the side. And eventually, for some reasons, I got invited to present something at a conference which was about Mizar, or it was in Białystok, which is where the Mizar team is.
Where is that?
Białystok in Poland.
Oh, really?
Yeah. So that's sort of like Mizar homeland, and so they had, and so I presented. What was it? I think it was Dirichlet's theorem or something like this while I was there. and when you meet people and then they say, oh, you should go to this other conference and whatever. So I started doing sort of conference stuff while still sort of out of academia. And at one of these conferences, I actually met Leonardo de Moura. He saw, me working on MetaMath stuff, and he was like, wow, it would be great if you could do some Lean stuff too. And I was like, I'd like to get a PhD. Do you know someone who you could? So he actually got me in touch with Jeremy Avigad.
Oh, really?
So Jeremy is at Carnegie Mellon University, and he's a professor in the philosophy department. And I talked to him, and we were clearly on the same wavelength. And so I basically, wrote in my statement of purpose, like, I'd like to work with Jeremy Avigad on Lean stuff. And my understanding is that that Jeremy was doing basically the same thing from the other side. So, so that's how I got my PhD at Carnegie Mellon. And there I was sort of doing Lean stuff.
So there you were actually one of the authors of Mathlib. Mm-hmm. What is the story behind that one?
Yeah, so I think I would say one of the major starting points for this was this big proof workshop in 2017 in Cambridge. There was a bunch of people there from several different proof assistance communities, and there was also a pretty influential talk from Tom Hales, which, if you ever talk to Kevin Buzzard, he'll mention that this was, the moment when he discovered interactive filters. Yeah. And he starts talking about, Lean to everyone. And then, that really helped with the adoption of Lean among mathematician community. But I guess at this point, this was toward the end of Lean 2. So, when I first started doing Lean stuff, it was Lean 2. And then there was this new Lean 3, which was under development. And so we needed a library for the material. And we had some stuff from the Lean 2 library, but for the most part, it was manually, there was just a couple things. And so it was really about okay, how do we build some kind of mathematics library inside Lean 3? And Jeremy, I remember Jeremy was sort of when I sort of suggested that, we could just make it open source and let the people deal with it. He was a little bit skeptical that anyone would pick it up very much.
Really?
No, and I mean, honestly, it's justified skepticism. I think that for most of during that period, ITPs are not that popular. It's
Which
not.
year is this?
This would be 2017.
17, okay,
yeah.
Yes.
So, I, especially among the mathematician community, there isn't a whole lot of adoption.
Oh, yeah.
And so it's this is all computer scientists doing, random little projects, and nothing ever really accumulates, right? And so even though, Metamath has a very sort of mathematical focus. It's ZFC set theory and proving theorems about stuff like that. But it's still a sort of individual it's rough. There's about 40 people who have contributed to it, and maybe 5 to 10 regular contributors. And so it's a relatively small project, all things considered, but there's still a lot of mathematics in it. And so, I mean, that was sort of what attracted me to it, as a sort of doing advanced mathematics in these kinds of systems. And so I wanted to replicate that in Lean to some extent. That's where we want to be, right? And I think it was, I think to some extent it was just good timing with, building up the Mathlib, and then Kevin Buzzard, are saying okay, we should get undergraduate mathematics, we should fill out the world, and I was saying we should fill out the mathematics world as well. And so that was really, I think, where it started. And so originally it was myself and Johannes Hölzel who were doing the maintenance of the library, and then later on the maintainers grew to 6 and then 10, and now I think it's somewhere around 30 maintainers. And the contributors just keeps going up. And I it's gotten to the point where I definitely don't know, a lot of the material that's just in there. but it's a really useful resource for people who, want to understand, pieces of mathematics. You can like click through and see how things are defined and so on. Like that's just a new resource that wasn't available before.
That is really cool, right? And I remember when I was talking to Kevin in an early episode, and he mentioned that he would teach this to the undergrads, and while they're trying to, like the summer, they're coming together and trying to solve some particular lemmas, and then they started submitting pull requests to Mathlib, right? At the same time. That's why I actually thought that because of that, Mathlib was actually his, right? Kevin, so it was actually you guys at CMU, which is pretty cool, very amazing.
Yeah. And I mean, it certainly wasn't us entirely. I mean, it really is a bunch of people from a bunch of different. It's been a global sort of project from almost the beginning. We have people contributing from all over, and it's always a nightmare to set up maintainer meetings because we live all over the world.
Oh boy! But how much of mathematics do you have a feeling of how much is it actually over there? I mean, in comparison to we have. I think when I talked with Kevin, he was pretty confident. Most of analysis, most of undergraduate mathematics is there these days.
Yeah, I mean, I think if you want to formalize a recent research text or something like that, for many areas, you'll be mostly covered. I would say that this is to a greater degree than it's really ever been the case, that you actually have the material there. I think it's really difficult to get precise estimates of this kind of thing because it depends a lot on what precisely, what it is that you're trying to formalize and whatever. But I think that the role of a library like Mathlib is to be able to provide that background theory, right? So that the thing that you're formalizing is the work and not the work and the mountain of stuff that it builds upon.
Right.
I think that's like a recurring issue with formalization of any kind, is that you find that, at least half of your work is building stuff that isn't in the material that you originally set out to do. Yes. You're just, 3 layers deep of yak shaving on, things that are missing. But I mean, it feels good sometimes to write that stuff because you know that you're contributing to something that will be useful for others. And, if you do this and other people do it, eventually you build up something useful. And I think that that's sort of how Mathlib operates.
That's beautiful. Is there some sort of, how's it called? Code, because when you're submitting code for another project, you usually have these directives on how the code should look like. Is there anything related to how the proof, the organization?
Yeah. So, I mean, it's definitely important to ensure that the code has, calling it good quality, I think is maybe not the right framing. It's not about whether it's good or bad quality. It's about whether it's maintainable and reusable and readable by other people. And so most of these have been encoded into the style guide for Mathlib, basically. So Mathlib does have a style guide, and it has certain ways of writing proofs in such a way that if they break in a contained manner, and it's easy to fix. And sometimes opinions differ about this, about the style of this or that. But I mean, for the most part, I think that people are pretty okay with the conventions. Although, I mean, I guess one interesting factoid relevant to the conventions is that between Lean3 and Lean4, the naming convention changed. In Lean3, everything was snake case, and then in Lean4, it became camel case sometimes. And so now we have the world's most complicated casing convention with a mixture of snake case and camel case and things like this.
Oh no!
I think that it's somewhat defensible in the sense that it is conveying information that is useful to the reader. But I think for the most part, we were just sort of trying to go with the flow in terms of, Lean is doing its thing, and then Mathlib is a somewhat separate entity. And so we would prefer to not have, if we went with our own case and convention and then users are using a combination of both, it just becomes a nightmare.
Yeah,
so then we have to, but I mean, a lot of that went into the design of Mathport, which was a tool that I wrote to translate Lean3 to Lean4 code.
Yeah, that's pretty cool.
Yeah.
Could you finish the whole translation at this point? So the whole Mathlib is Lean4 these days?
Yeah. So to give some context on that, so as I mentioned, Mathlib started out in Lean3 near the beginning of Lean3, and then Lean4 was, it came around slowly over the course of about 2 years period, where we sort of knew that it was coming, and then we had like unreleased, there was a GitHub project with stuff on it, and then, we were getting closer to something we want to call a release. And during this process, we talked about what exactly to do with Mathlib, and we decided we'd port it rather than, like, between Lean2 and Lean3, it was not really a port. There was the old library, the new library, and we sort of manually wrote what we wanted to. And then eventually, it subsumed the stuff that was there. But here, like, we've already got so much stuff, it's like, it would not be feasible to do it any other way. And so we went for a port. And as far as I'm aware, this is the largest, like, porting effort that has ever been done on interactive theorem provers. We ported about 1 million lines of code from Lean3 to Lean4. And most of that was done through this tool called Mathport. And the idea is that it reads in Lean3 syntax. I had to modify Lean3 to produce an abstract syntax tree. And then it would walk over that abstract syntax tree and produce Lean4 abstract syntax.
Okay.
And so, like, half of the program is in Lean3, the other half is in Lean4. They communicate over JSON,
That's
awesome. Yeah, and
so you also, this is a curiosity from someone who's also done some work doing this kind of translation. When you're reading in a proof, you have the context, like, you have access to the context in order to translate whatever is the next tactic. Kind of
yeah. So in Lean3, we have the context.
Right.
In Lean4, we may not be able to reconstruct the context because we're generating code that may not be correct.
Gotcha.
So in particular, this translation was really focused on doing source-to-source translation. So, like, if it sees simp, it produces simp. And it doesn't matter if the simp produces a different result. We want to preserve the intent of what the user originally wrote. Because if we were to say, okay, if it doesn't produce the right result, then we'll replace it by its underlying proof term. Well, then that will generate, like, a massive spew of garbage. And then the person who's actually doing the porting is going to have to see that, delete it, replace it with a simp, understand why the simp is broken, and fix it anyway. So that's why, it was really focused on making it sort of look good and not necessarily to work correctly. But it would still work about, like, 95% of the time. And that's, like, enough to, allow a person to manually clean up the rest. And basically,
although I'm very sure that when it doesn't work must be very painful.
Yeah, you would bring up the Mathlib 3 and then the Mathlib 4, and then you, like, step through the Mathlib 3 and the Mathlib 4, and then you see what happened. And, and there were a lot of PRs to Lean4 at the time as well. Oh, this changed. Was this on purpose? Should we change it back? These sorts of things. But it worked out in the end. So we ported it, like, basically there was a slow period of about 6 months where we were sort of doing some manual porting and writing this tool. And then another 6 months, like, mostly over one summer, I think it was the year before that, I think, when we just, like, unleashed the horde of porting, all the people on the Zulip, and, ask everyone to just copy a file over. We've got the system where it will generate it will run the porting tool on all of Mathlib 3. We generate a bunch of files, and then, it give them to people to PR to Mathlib 4. And so we just, you can see it in the graph of, like, if you look at the graph of, like, the size of Mathlib, there's this period where it just goes right up, and that's when it just got filled out. But yeah, and it did make me sort of hopeful, I would say, for future projects in this vein, that, like, source-to-source translations aren't impossible. They are actually doable with some work. And, I would like to see more source translations. Like, I've done a lot of stuff about like low-level translations, but source-to-source translations I think are also interesting. And they have the advantage that like users can build on them, right? They produce an artifact that people want to use directly and incorporate into their systems, rather than the low-level translations, which they can be used as a sort of like FFI kind of thing. Like they're an external library, but you wouldn't want to touch it. It's some auto-generated garbage. So yeah, with here you really have to focus on making it like look good too, right?
We were actually talking a little bit about this earlier over coffee, but another point that I was mentioning that highly interests me as well is having this notion of, okay, so you have these two languages, like in this case, Lean3 and Lean4, and a particular question that I feel that it's not particularly well targeted in academia right now, we don't have many papers about it, is that of, kind of comparing the expressiveness of these two languages, these two type systems, what is kind of like provable in one, or what is, you can show that it behaves in a particular way, right? So for example, if you have a port from C to Rust, for example, that would be pretty cool, but clearly there is a difference in the semantics in these two languages, and how do that compare? How can you make this comparison and this thought in a modular way, and what are the processes that I think it definitely deserves some attention, would be very interesting too.
Yeah. I mean, so I have some thoughts on, like, as it relates to ITPs. I mean, there's definitely a lot of research that has gone into, like, logically, what are the differences between, higher order logic and calculus of inductive constructions, and ZFC set theory, and these sorts of things, right? This is the stuff that logicians have been looking at for the past 100 years.
Yes,
we have some good answers to, who's stronger than what, and so on. Things like, good old incompleteness theorem also tell you bounds on, like, okay, this is strictly stronger than that because this one can prove that one's consistency, things like that. But on the other hand, I also think that to some extent it misses the point that, like, when you have these systems, I like to describe them all as sort of math complete. They all cover basically the things that you want to do in the course of regular mathematics. If they didn't do that, then they wouldn't be working out as ITPs, right? So, Hull Light can do this stuff, and Agda can do this stuff, and Lean can do it, and it doesn't matter that they have different consistency strength. What really matters is whether they can, construct things like natural numbers and topologies and whatnot. And so that's where, when you have like source-to-source translation, it's really explicit that, like, okay, we're not trying to be complete in the sense of, like, we're not going to translate everything in the source language to everything in the target language. We might miss or slightly, not accurately translate some things, but we're still going to, like, get the gist of it across. And I think that that's usually what, like, when people translate plain math, like informal mathematics onto the computer, they're usually translating the gist, right? They're not really translating precisely the details of what the oftentimes the details are, vague and or inconsistent anyway. So it's not really worth it to try to encode those. And so in that sense, if you want to go from one system to another, taking more than the gist is maybe like taking artifacts of your original formalization, right? If I take some proof and I put it in Lean, do I really mean it to be a proof in ZFC plus omega inaccessible cardinals? Probably that wasn't important, right? That was just something that came along for the ride when I put it into the system, because that's the axiomatic system that happens to be working with. If I was doing it in Agda, it would be a different, thing. But I probably could have still completed my proof, right?
And sometimes even you have to change the sketch of the proof, like how the approach, the way that you're proving, because it's the same thing as a different paradigm, right?
Yeah.
Change the axioms, or change the way that you're actually thinking about the proof of the
definitely the way in which proofs are expressed does differ from one language to another. A popular example of this is if you don't have dependent types, then you're going to be using predicates for more things that you would have been using types for in a dependent type setting, for better or worse. And, the idiomatic patterns absolutely differ from one language to another. And in some sense, that's sort of the hard part of doing these translations. If you want to get like an idiomatic translation, you have to translate type classes in Lean to canonical structures in Puck or something like this, right?
Right.
It's all mathematically, the same, basically, but
the flavor changes.
The details change, yeah.
But okay, so coming back to Mathlib, I remember when I was talking to Kevin Buzzer, I think they were about to start the project to formalize for Maslow's theorem.
Yeah.
Do you know how's that going? Is that finished?
Not finished yet. As a matter of fact, it's been fairly quiet recently, and the reason I think is that maybe Kevin announced it slightly too early. His grant starts in October, so
it's still going to start this October.
Yes.
Okay.
Yes. Okay. It will be opening up very soon, but right now he doesn't. He has like a very basic sort of. It has a blueprint, but the blueprint is still vague on a lot of details.
Of course,
and a lot of the foundational stuff is mostly going into Mathlib at this point.
I'm surprised actually, because I think they were starting this project like 2 years ago, and now the grant's opening.
Yeah, well, so the thing was first announced, or like the blueprint was released, I think, at the end of April. And the project, it's been quite some time, but I guess getting grants takes time.
Sure. Yes, for
this
sure.
sort of thing. But I'm very excited to see how it goes, and maybe also contributing to some extent. I think it's a really cool theorem, and it's nice to be able to contribute to a theorem that the layman knows, even if the proof is maybe not that accessible.
I have a listener that was talking in our Discord the other day that he has this strong conviction that the whole reason of being of type theory for all is to advertise Lean. Honestly, I personally do not care which theorem prover win the battle, whatever, if it's a battle or whatever. But I personally feel that Lean is an extremely exciting project, exactly because mathematics, the people in math adoption liked it. There's something being done right for them in some sense, right? So this huge, proving the Formalizing theorem in Lean is an extremely, extremely exciting project. And I think it's something that is a game changer for the community of interactive theorem provers, which means that all of our community, anyone doing programming languages, anyone doing type theory sort of thing, it's something that is gaining attention, particularly when we have the most brilliant mathematician tweeting about this, right? Terence Tao doing all of those stuff. That was awesome. That was really cool.
Yeah, seeing Terence Tao getting involved in Lean has been really interesting. It's like these are people who I knew as heroes growing up and whatever. And it's like oh wow, they're real people, and they love Lean too for some reason.
This is kind of how I feel being here in Chalmers. Meeting all these great professors, these great people in person. You actually exist? Oh my god! That is very, very awesome. But okay, so that is Mathlib. You mentioned that there is this port that you developed. Is this? I have this feeling that this was the beginning of Lean4Lean, because there's definitely some metaprogramming here going on. What is?
Yeah. So Lean4Lean is the origin story of Lean4Lean is basically my master's thesis project. And so this was. I've been using Lean for some time, and I also have these sort of logical leanings, and I forget exactly what prompted me to do it, but basically, I wanted to get down, I think it was like trying to understand what Lean is. I have this sort of draw to really dig down into the details of a system and, not just use it because, it feels like it's a proof assistant, and really understand how does it tick, right? And with Lean, well, I mean, if you follow the threads enough, you get down to something that they call, calculus of inductive constructions. They say, oh yes, this is based on the calculus of inductive constructions. And then you look up at what that is, and then you look at what Lean is doing, and then they're different. And then you ask the question, okay, why is it different? Is it different for good reasons? And are those, what's the real origin story here? And, the answer is, well, it's not just CIC, it's CIC, and then also we wanted proof relevance for reasons, and then we wanted, we wanted the universe hierarchy because that's how they do it in CIC, but we didn't want to have, template polymorphism because we saw how that went in Coq and it didn't go so well, so we thought we'd do better. And so basically there's a bunch of very path-dependent historical things that end up leading an interactive theorem prover like Lean to pick some particular strategy of axiomatization or the underlying type theory ends up being some particular thing, but because of historical factors. And if you look at exactly the same thing for Coq, it's going to be different. People, there was one person at one time who asked about this inductive type and they pointed out some issue and they were like, oh, maybe this guard shouldn't fail in this. And then something changes in the kernel and then now it becomes part of the theory for everyone to learn, right? I don't know. It's a very sort of evolutionary process, how these ITPs grow. And so I wanted to just understand, what is Lean? Can we write it down somewhere? So I wrote it down somewhere. My thesis was basically, what is the type theory of Lean and what are its properties? And so I think, okay, page 1, let's give all the axioms and then we'll be done. And then you can refer to that, and that can be, a reference for what is Lean. And I would say it was pretty successful for doing that. I mean, the last page is, oh, and by the way, Lean is consistent because it has a model in ZFC with countably many universes. So that was the other important thing that I wanted to know about this theory was that, okay, it's doing something and it's consistent, right? And not even just that it's consistent, but it has a natural model, right? The model is the one where types are just sets and elements are elements of those sets. It's the very obvious, straightforward model. You don't have to futz around with strong normalizability and these realizability topoi or anything like that, right? None of that stuff. I don't understand that stuff. Let's do the basic thing.
So wait. So your master's, where was it? We were working with.
This was with Jeremy Avigad.
Oh, so you did your master's and your PhD?
Yeah, I did them together. Okay. Yeah.
And how did you get access to all this information about Lean? Because you'd have to work very closely to Leo, I assume.
So I didn't work that closely with Leo. This was basically, I read the code. And,
wow.
Yeah.
That's a lot of work, man. I'm impressed right now. You're very patient.
This is a lot of it was sort of folklore. But and to some extent, it's also an idealized account of what Lean's theory is. It's sort of what Lean's theory ought to be. And there is some stuff there about how the actual thing that Lean implements is a slight under-approximation. In particular, one of the undesirable properties of Lean's type theory is that it has undecidable type checking. At least the idealized version of Lean is undecidable. So then you ask, okay, but Lean is doing something, right? What is it doing? And the answer is that it's doing some under-approximation. It will sometimes say that something is not type correct when actually it is if it went and ran a Turing machine for forever and then found out later. It would not be practical for it to answer yes. But it can, there's some reasoning there. And so if you look at the type theory that Lean is sort of actually implementing, that one fails in different ways. The definitional equality is not transitive, but it's not transitive in cases which are so weird and obscure that no one ever
You're never going to hit that counterexample.
On purpose.
Yeah.
So that was me trying to describe what is Lean as some mathematical theory, prove its properties, and so on. Lean4Lean is a recent project that I've been working on, and it's essentially, let's take that and formalize it, because that was just a math paper essentially. It was
right,
just,
yes.
I wrote down some proofs and I said the rest follows exercise with the reader, or, the usual.
Right.
And now I have to be the reader and do the exercise.
Right. So then you formalize all of this in Lean itself. And,
exactly.
Right.
So Lean4Lean, more precisely, what Lean4Lean is it's a project that contains a kernel, and that kernel is essentially a carbon copy of Lean's actual kernel, except written in Lean instead of C++. So, it's been written in sort of functional programming style, and also with some effort, but not too much, paid to like making it formalizable, like using pure monads and stuff like that when possible. But otherwise, it's like literally, like you can do differential testing. You can run the C kernel with tracing, and you can run the Lean kernel with tracing, and then you can watch them do exactly the same steps in exactly the same order, right? So that was important for me, both for testing purposes and also because it means that if I find a bug in the Lean kernel, then I'm pretty sure I found a bug in the C kernel too, right?
Really?
So that's sort of a way, it's not clear to me whether this Lean kernel will become the official kernel in the future. It would be nice if it did. I tried my best to make it efficient so that it is usable as such potentially, but it is a little bit slower. But even if the original kernel is kept, having this kernel and then having verification, having proofs about it will allow us to have good confidence about the original kernel as well, right? So yeah, so it's this program that you can run, and you can use it to check existing Lean. I've used it to run on Mathlib. It actually works at scale.
Right.
And then there's the other half, which is the type theory. So now I have to define, okay, what does it mean for something to type check? And, what is this type theory? Basically all of the stuff that was in the paper. And then also, does it have the properties that it claimed it has? And it's been interesting sort of poking at, the proofs and the informal proofs, seeing whether they actually translate formally. And sometimes the answer is, there was an additional complication here that, maybe my exercise to the reader wasn't quite as obvious as I thought it was. As usual. So yeah, I've been bug fixing my own code, basically.
That's nice. Okay, good.
But yeah, it's still underway, but I guess if there are any people who are interested in doing meta theory of proof assistance or of type theories, then it's absolutely willing to to get help on this.
Yes, absolutely. How does it? I don't know if you know entirely, but in Coq there is a similar project, MetaCoq, that does something very similar. I think in 2018 they have a very good paper about it, showing correctness of Coq inside of Coq itself. How does it compare, Lean4Lean?
Yeah. So they are basically, I would say it's essentially the same project, but for Lean, right? There are a little bit of differences in that, besides the fact that the theory itself is different, MetaCoq also has something called template Coq, which is for being able to do verified metaprogramming, which is a cool extension. But currently isn't a goal of Lean4Lean. Coq also has, so I would like to borrow as much as I can, obviously, from MetaCoq in terms, or vice versa, right? To see whether they are very similar theories. They ought to have similar, proofs of correctness or of, various kinds of well-formedness. And actually, it's complicated, as should come as no surprise. Coq has cumulative universes. Lean does not. So this changes, how the definitional quality relation works. How
does it work in Lean?
So in Lean, you have a hierarchy of universes, and then each term has at most one type. So up to definitional quality.
Okay.
And so this property is called unique typing, and is really critical to the structure of the thing. And it's also the hardest proof in the paper, and the one that I have yet to verify. But so that's really important. In Coq, not true if I just say it like that. Like one term can have multiple types that are not definitionally equal. However, it will have a principal type, and then there's a subtyping relation. So Coq has a subtyping relation, basically, and Lean doesn't. But on the other hand, Lean has proof of relevance, and it has sub-singleton eliminating inductive types, and these create havoc for the theory. This is the reason why the type theory is undecidable, and that means that you have to get clever in other ways in order to prove properties about it. And so there are aspects of that. And then also the fact that the reduction relation is typed, that is to say you have to know what type something is in order to know how, like what things are definitionally equal or not because of proof of relevance. So proof of relevance says that two things are definitionally equal if their type is a proposition. So you have to know what their type is. And so you're sort of doing type checking at the same time as your definitional equality. In Coq, those are done separately. Like you can define an untyped reduction relation, and then the definitional equality is defined based on that. And then you can define typing on top of that. So everything is sort of layered, and that makes things a lot easier to analyze. And so the hard part with Lean4Lean is really trying to untangle this like giant nested, induction of like all of these properties that are sort of, they seem like they should all be true, but also proving any one of them implicates all of the others. And so, it's unclear where to start. But yeah, if they are true, then, then it should be possible to prove the correctness of Lean's kernel with respect to the semantics. And so that's the goal.
There is something that people complain a lot about the type system of Lean. It's something related to things not being strongly normalizing, and this makes things, this is the same stuff we're talking about. Because I remember also hearing something about quotient types that things break, those discussions? Yeah,
so basically the undesirable type theoretic properties of Lean are failure of transitivity of definitional equalities, I mentioned, failure of subject reduction. That means that if you take a subterm and then you replace it with something definitionally equal, then it continues to be well typed. This is true for the idealized theory. It's false for like the actual, the algorithmic implementation. The other one is failure of strong normalization, or even weak normalization, I think. So this happens because there are ways, this is actually a recent, well, not that recent now, it's maybe a year and a half old, proof by Coquin and Abel, which showed that there is a counterexample to strong normalization in the presence of proof of relevance, and I think that might be it. The construction is extremely simple, but it basically allows you to construct a non-normalizing term inside prop, which is weird because you would never reduce something inside prop, or at least that's what I thought. But it's not true because in Lean, you can have inductive types that are in prop, but eliminate two types that are not in prop. So that means
is that large elimination?
So yeah, that's large elimination. Yeah. And when you have these kinds of funny types, then you can trigger non-termination even for defining like closed terms of type NAT.
Right. I think that's just completely forbidden in Coq. If you try to do the pattern matching like that, it just fails.
Exactly. And so Lean's definitional equality allows it. Lean actually won't reduce it. That's the reason why it's under approximating. So it will just get stuck on that term, but then you won't get your number out, right? So if you define some number by recursion, then it's just going to get stuck.
I'll make a quick stop here to mention something that we were also talking earlier on, which is I have this dream that at some point someone will write down, maybe I should just do the research and do it, but I'm lazy. But someone will write down all of these interesting properties and how they, like these axioms and how they relate or not to each other, like this very nice big blog post that explains all these axioms that we're talking about right now, large elimination and injectivity of type constructors and normalization. We're not going to spend too much time right now trying to define any of that. Otherwise, it would be like just a whole class on those things. But you can Google all of those stuff. I'll try try to put some links in the description of this episode. But sorry, I interrupted you.
Yeah. I mean, so there's basically a whole bunch of design decisions that one has to make when constructing a dependent type theory. Like even after you've decided, I want to make a lean/coq/agda-ish thing, you still have to make a bunch of decisions. And those decisions impact whether you have all of those properties, and it often in quite subtle ways. And honestly, I'm not even sure that the whole space is really all that explored. I mean, it's difficult to, analyze one of these theories, let alone, the whole
That's what I'm saying. Like we should have this table so we have it in one single place how these things relate, right?
Yeah.
So that was Lean4Lean. Is there anything else interesting? I think for Lean4Lean we tackled everything. So we should spend a little bit of time talking a little bit of Metamath Zero. As well. What is Metamath? What is Metamath Zero?
Yeah. So my PhD project was on some almost entirely different subject from all of this lean type theory stuff. The idea was I wanted to have a language that allows where you can prove the correctness of a proof assistant for it. So like Lean is a really complicated system, and I am now in the process of trying to prove its correctness anyway, because it's a really, important in practice system. But it would be nice if we could have a system which was still good, is still efficient enough to do good projects, but also had some really strong guarantees about, the correctness of the system. Because why is it that I should trust, Coq or Agda or Lean? These are all huge code bases, right? Every single one of those is really monumental. And it's been developed over a long period of time, and it makes these strong claims. They're interactive theorem provers. People will say things like, oh, if I prove it in the system, now I know that it's true, right? People get these sort of, unless you're specifically thinking about it, well, it's something to introspect on. It's like, are you sure?
Really?
There are good reasons to distrust that, it's a product of humans like everything else. People make mistakes in compilers, they make mistakes but it's like, I don't know, people have blind spots when it comes to the implementation of the language in which they're writing. They just assume, oh yeah, no, there wouldn't be a bug in that. The bug is in my code. It's not in the code that runs my code. But yeah, these are also absolutely worth investigating. So I thought, okay, can we get a language which allows you to prove its implementation correctness? Now, this is something that I think the usual thing that people will ask or question in response to this is wait a minute, I heard about Gödel's incompleteness theorem, and it says you shouldn't be able to prove the correctness of a system in itself. That's true, but what we're actually trying to prove here is when I say implementation correctness, what I mean is you can prove that it's some program, some concrete program, even more, it's a sequence of bytes in the x86 or something like this, right? And I want to prove that satisfies the specification of a theorem prover. Now, what's the specification of a theorem prover? Well, it takes in axioms and theorems, and then it checks that the theorems follow from the axioms. So if you give it a proof and it says yes, then that proof should be correct, and the theorem should be following from the axiom. What this doesn't say is that you can't prove everything because the axioms you gave it are inconsistent, let's say. You are perfectly capable of giving inconsistent axioms to a correct theorem prover and getting falsity out. So because of that, this is actually not a theorem that sort of implicates Gödel in any way. You can prove it in just basic, you can prove it in piano arithmetic if you wanted to, right?
It's a weaker form of what Gödel's inconsistency is talking about.
Exactly. Okay, so what is Metamath Zero? So I took Metamath. So Metamath, I already mentioned, is the system that I sort of grew up on, and it does a lot of things differently to most ITPs. But one of the things that really struck me about it is that it's just so much faster, and it really clarified for me some of the things that ITPs do, and where we could be, and the degree to which we actually are falling short of making something that's sort of hitting the large scale limit of where we want to be with theorem provers. Right now, we're like 5 or 6 orders of magnitude away from what we could be doing. And so this is why it's like, okay, let's try to take those good ideas and then distill them into something that still has those properties so that we can really, run this stuff at scale. And then you get a simple system where you can do theorems, you can do definitions, and that's all that's really needed for doing mathematics. And then have tactics for generating, theorems about, you give it I define the specification of x86 as some kind of theorems and definitions, and then we can say, what does it mean for programs to be correct? And then we want to prove that with respect to a specific program. So how do we generate a piece of, a bunch of bytes that are describing a program and then proving properties about that? Well, we need a compiler. So I needed a verified compiler. So I didn't have a verified compiler. So I needed to write a verified compiler. So that's yet another portion of his project, which keeps growing in scope. I have a verified programming language within which to write the kernel that I'll be doing the checking, right?
Okay.
Because I need to have a type checker for this language.
Right.
I mean, I wrote an unverified type checker in order to get things started, but
then you bootstrap and now you get.
But now I want to have a verified type checker. So I need to write it within a language which allows you to state proofs. And so this is something that I was telling you before our coffee, but I think that the world is lacking in programming languages that are designed for proving program correctness proofs. I think that this is the task that comes up routinely, and it's a task for which we don't have enough good options, especially if you have performance requirements. Like using functional programming for doing for verifying program correctness is all well and good, but it might not actually be applicable to the original situation that you've extracted the problem from. Like if you're trying to write like an OS kernel or something like that, that isn't going to cut it, right? You need another mechanism. And what most people are doing nowadays is some variation on, we write C code and then we prove the C code is correct through a very convoluted sequence of steps. And this is an incredibly painful process. It involves taking your code, turning it into an AST, putting the AST in like coq, and then proving facts about your incredibly encoded statement.
Right.
This is not a system that was designed for users. Right. This is a system, this is like an academic style project, right? This is something where you really haven't thought about the user experience side of things. What we need is a programming language that is really designed for people to be able to write programs with functional correctness proofs. One of the languages that I think does the best at this is Daphne. So I don't know if you're familiar with Daphne, but it's sort of Java-esque, and it's got like requires and ensures, and it uses
it's a horsepower logic.
Exactly. And you're using a SMT solver in order to solve all of the individual proof goals that come up after every line or something like that. This has its own downsides though. It's not an ITP, it's an ATP-based system, automated theorem program. So that means that you can run into issues with the fragility of the proofs because they're not really proofs, right? They're more like they're goals. They're goals that you're giving to a system that usually gets the answer right. And you don't store the proofs. You just remember what the goals were. And next time Vampire gets an update, you might not be able to prove the things. Or, if random things get permuted, then, things can fail.
Yeah, usability of SMT solvers is not the best in the world right now. Debugging it, like taking the output of what is going on under the hood and trying to make sense of how to fix things is, and also this idea of how just permuting a for all with or two variables, things start going crazy. It's weird.
So I've seen people talk about, we were doing some proof of some big Daphne program, and then they tell you the horror stories of like having to deal with this, and I'm like, I'm not sure I want to go there, right? So I'm the direction of this programming language, which I called Metamath C, is to really have a ITP plus a C-like programming language, right? Or Rust-like, actually, with some separation logic thrown in there because it makes correctness proofs easier. So it's sort of a cross between like having this really well-defined machine model that you get with C, like, okay, so C is not actually a low-level language, but it has that, it gives you that feeling of like, I know what the computer is doing. That you don't get that feeling. You get that feeling with C++, you get it with C, you get it with Rust. You don't get it with Haskell. You don't get it with ML. Because there's a bunch of things that happen between your code and what runs on the machine, and then you're debugging space leaks or other crazy things that like they wouldn't happen if you were able to tell the computer what to do. If you're using an imperative sort of paradigm for really controlling, like that's sort of where imperative languages shine, is the performance aspects. Like you have control over what it's doing. Whereas the functional programming languages, they excel at the specification angle, right? Yes. They allow you to say what the program does, but not so much how it does it. Right. And then trying to get something that does both is historically been the hard part. Yes, right. Honestly, I think that Rust has done the best in terms of being able to merge aspects of both of those things in some usable way. And so that's sort of why I sort of drew a lot of inspiration from Rust for this language.
Okay, so Metamath, is the original Metamath also imperative?
So Metamath is a proof system. So it's not even a programming language at all.
What's the difference?
So only the dependent type theory based systems have this, you could call it Curry-Howard isomorphism, like this notion that something is simultaneously a program. And there are a lot of other sort of traditions of mathematical formalization where that's just not a thing. If you start from first order logic as your principles, that's not a thing, right? You have proofs, and they're proofs. They're not programs, they're proofs.
They're proofs.
You can have proofs about programs, but the programs are really something separate. And I actually am sort of on that camp where I would say that proofs aren't programs, and if you do try to make your proofs programs, you end up with things that are simultaneously bad proofs and slow programs.
Yes. Not to say about dependent type hell as well, that, like this humongous dependent pattern matching just
exactly.
makes no fucking sense.
Yeah, I mean, one of the things that you get with dependent type theory is like these cast operators. That's sort of what I consider the origin of this dependent type hell, where you have a term and you want it to have an equal type, but it's not definitionally equal for whatever reason. And so you have to convert it from one to the other. But now you do so via a function. And now that function is in your term. So now if you want to prove a property about the term, it's not the same term anymore because it's got this function wrapped around it. And so you have to, and then you have to make more casts to uncast your casts, and everything becomes much worse. And in these other sort of like soft typing systems, you don't have this issue. You just, or like extensional type theories are in a similar camp where it's like you just don't have casts, and instead you have typing assertions that are sort of floating about.
Let's take a break here and come back tomorrow to talk about, go deeper into the meta theory of Metamath, Metamath Zero, this really dig into the meta theoretical details.
Yeah.
So I'm gonna stop here. Let's see. All right, we are live again, one more time in person. This is tomorrow for who is listening. We took a short break of 24 hours. And now we are back, and we're back to talk exactly about Metamath. And we want to get our feet wet again and start slowly by taking a step back and really understanding what is Metamath and understanding what is the goal of Metamath and how things work. Because in these 24 hours that we have been absent, I actually decided to open for the first time Metamath Wikipedia, and I was so scared. There was so many dollar signs and FC axioms and these little things that for me doesn't make any sense anymore. So should we start from there?
Yeah, sure. Yeah, so MetaMath is it's a 30-year-old system now. It was created in 91, I think, and it has a lot of interesting design choices in the way that it was set up. Not all of those I agree with, but the ones that I think are the most relevant for, let's say, the new user's perspective on the thing is, well, the keywords are very bare bones. So you've got $C, $F, $P.
$A was an axiom.
$A, yeah. So all of the keywords are a $sign and then a letter. This is, however, very easy for parsing. One of the really interesting things that you can do with MetaMath is you can parse it using the Python split function. That's a parser.
Wow, that's a hard one.
It's just, spaces. That's it. These are basically the decisions that make it easier for a computer to parse it, and it makes it easier for a programmer to write a verifier for the language. But obviously, some of those decisions come at the cost of readability, right? Another one is that because split is the tokenizer, it means that all of the parentheses have to have white space around them, which means that and it ends up being very,
oh God,
very
sort of languages
spaced out, right? It's maybe not a decision I would have made, but I do think that it is valuable to have a proof assistant that really optimizes for ease of implementation of a verifier, right? Because that's a different design space than you'll see most of the time.
Right. Let's go deep into what does that actually mean. And I'm assuming my listeners, and I'm assuming this because it's an assumption about myself, we are only aware of how proof assistant works, and it seems to me that MetaMath is different. It's not exactly a proof assistant.
Well, so what I would say is that writing a MetaMath verifier is like baby's first proof assistant. It's, it is a weekend project. You can get it done very quickly. And while doing so, you will learn about what does it mean to check a theorem? Like, what is a theorem? What is an axiom? Like, how is it that you build up an axiom by sequences of rule applications, these kinds of things. So it's, just the bare core concepts that you need in order to implement something that looks vaguely like a proof assistant.
Okay, so for that you have then axioms and then rules. What else do you need?
Yeah, so the core concepts of MetaMath are that, statements are sequences of tokens. A token is a constant symbol or a variable. Both constants and variables are pre-declared. In particular, it's not a tree. This is one of the weirdnesses of MetaMath. It's not a tree of symbols. It's literally a string of symbols, just a string of tokens, which can either be constants or variables. Now, given one of those, you can substitute into that string. You take one of those, you take all the variable occurrences of some variable, and then you replace it by another string. Okay. And then this gives you another string, and the thing that you replace it by is going to be another string of constants and variables. And so the meta in MetaMath actually stands for meta variable mathematics. And so the idea is that you have this pervasive use of meta variable tokens, and then they just sort of stick into others and so on. So the application of one rule is just you take a theorem or an axiom will have the form that it takes a number of hypotheses. Each of these are statements, and then it has a conclusion. That's also a statement. And the hypotheses and the conclusion are going to have some variables, and then you say how you want to substitute those variables, and then you apply the substitution, and then as long as the hypotheses are proved on previous steps, then the conclusion is. And that's the quote-unquote one rule of MetaMath. So whenever you do a proof, it is a sequence of you select some theorem, and then you apply the substitution and previous steps, and then that gives you the next step, and then you just do this over and over and over again until you get to the statement of the theorem statement itself from the hypothesis. And so that's how you prove one theorem, and it also has that form where it takes a bunch of assumptions and then produces a final statement. And then you repeat that process to produce each theorem, right? So you have a bunch of theorems in a file. And that's the whole thing. That's all there is to writing a verifier and checking Metamath theorems. Rinse and repeat for, 50,000 theorems and you have ZFC set theory.
Okay. It's very mind-blowing to me that you can have so much with so little.
Exactly. I think that is really the thing that is, eye-opening about Metamath is it's not just that it's simple. It's easy to write a simple system. Mm-hmm. What's interesting is that it's simple and it also works at scale. We have, a proof of the existential statement now that it is actually possible to build a practical system on top of incredibly simple foundation. And so that's really stuck with me when I move to other proof assistants and so on. I see how everyone is doing things. I'm remembering in the back of my mind, how Metamath does it and how you literally don't need much at all, right?
So you actually learned Metamath before everything else.
Metamath was my first proof assistant.
That's so odd, man. Nobody does that.
Yeah. So, it really, it, especially when you see okay, these are the core requirements. And then also, so I mentioned that Metamath is fast before, and I wanted to be a bit more specific about that. So currently there's a file, again, this is an interesting design choice, but all of ZFC set theory exists in one file, which is 400, maybe 500,000 lines.
Holy shit! Why?
One file called set.mm, and it's just got everything.
I think my Emacs would break if I just open that.
Yeah, so you do need to have a text editor that has support for large files to edit this thing, but they do exist. And that file, it contains a comparable amount of mathematics to many of the proof systems. It's up there on the rankings of who's proved, how many theorems of whatever. And this can be checked by the sort of the OG Metamath, the Metamath.exe, which is the original Metamath implementation by Norman McGill, in about 10 seconds, right? And with a optimized, rewrite it in Rust style verifier, this has been improved to 1 second.
Wow.
So you can do much better if you optimize your data structures and so on, in order to get fast verification of this file. But if you compare it to Mathlib, which is Lean's library of stuff, that takes an hour, maybe 20 minutes if you have a very fast computer. It's not in the same ballpark, right?
I was talking to Shipala one time and I asked him, on his big projects and projects that he has very strong LTEX for searching proofs. He said that a file, some of those projects can take a whole day to compile.
Yeah. And I'm working here on CakeML, and CakeML is also a project that takes 24 hours to compile. And it's it's a very long way from my origins. Let's just say, right?
Yes. Mm-hmm.
So I'm constantly in this mindset of screaming in my mind, surely, this is not necessary, right? We've done something horribly wrong as an industry if we end up with all of our systems producing 24-hour projects. And I think it's fundamentally going to limit our scalability. When it comes to, if we really truly accept this grand vision of having formalization everywhere and doing all of this stuff, this is going to be a major roadblock. If you compare the compilation time of Lean to the compilation time of C or of Rust or of any other proper, just a regular programming language, it's night and day, right? No one, a programmer is not they expect to compile 1 million lines of code a second, right? They want that kind of speed. And what we're delivering is not anywhere close, right? So that's something that we have to keep in mind when we're sort of imagining that we can somehow get to that demographic.
So then, Is that what you had in mind when you started working on Metamath Zero?
Right. So that was part of it. So when I started working on Metamath Zero, one of the things that one of the reasons why I didn't want to use Metamath for the project was that although it is a very simplistic thing, and that sort of ticks one of my boxes for what I needed from the system, it has a slightly weird meta theory. One of the things that I already mentioned is the usage of strings. I think that's it's actually a performance issue because the way, there are mechanisms that you can do to be able to prove things which take advantage of the fact that you, for instance, if you had an ambiguous grammar, that is to say, if I said that, let's say that if I have a well-formed formula, phi, then phi arrow psi is a well-formed formula, but I don't put parentheses.
Mm-hmm.
Then if I have two arrows in a row, in Metamath, that simultaneously means both associations of the thing. You can apply theorems that make the assumption that it is parenthesized one way, and you can also apply theorems that imply that it is parenthesized the other way, right? Yeah. So this would allow you to... So basically what that means is that ambiguities in the grammar become soundness critical, or unambiguity of the grammar is soundness critical. And so you have to have mechanisms to somehow check ambiguity. These do exist for set.mm. But it's still an extra thing, right? And one of the things that I would like from a kernel is that it checks all of the things. It doesn't check most of the things and then leaves the other thing to be checked by humans or by some external tool.
So just to be clear, then your grand vision here is to have this very minimal kernel that is extremely fast. What are your...
Yeah, so I want a kernel that's fast, and it also provides guarantees. When a theorem prover claims that a theorem is proved, you should be able to derive some fact from that. For instance, if I want to be able to write a statement of Fermat's last theorem, let's say, and then stick it in a file and say, anyone is allowed to, I want to give a bounty on the first person to prove the theorem, right? Yeah. And so it's okay, I give you the statement of the theorem, and then as long as you can somehow fill that in, automatically deduct from my bank account, whatever. Okay. I don't want someone to be able to hack the system in order to get my money. I want that the only way for them to get my money is for them to actually prove the theorem, right? Okay. So I think
so. You want to develop a smart contract language.
Yeah. I want a system where you get those guarantees. Okay, right. I think that's one of the things that people that's a really strong way of phrasing it in terms of monetary gain. But I think it really makes it clear what one should consider as the attacker model for this kind of thing. A proof assistant is supposed to ensure that these things can't be broken, right? That's the purpose of the software. So what can we do to accomplish that? So one of the issues with Metamath was that it didn't have checking for grammar ambiguity, and it depended on grammar ambiguity for soundness in these ways. Another issue was that it doesn't have a concept of definitions. So in Metamath, definitions are basically axioms. You introduce a new constant symbol, you introduce an axiom that says that the constant symbol is well-formed, it has, the typing that it's supposed to have, and then you introduce an axiom that says what it's equal to. It says, whatever equals something, and all of those axioms are load-bearing in the sense that, you could screw them up in some way, and then you could prove false, of course, because they're just axioms, the system's not checking them. But at the same time, you don't want to have thousands of axioms on your goal. I proved Fermat's last theorem relative to these 10,000 axioms, which are actually definitions, right? Now I have to go and look through all of them and make sure that they're all reasonable. It would be nice to have, a fixed list of axioms, and then the definitions you're allowed to introduce them as much as you want. So again, in set.mm, there is a mechanism to solve this. The definitions are checked for conservativity. There's a trivial syntactic check that says basically, you introduce the new symbol on the left-hand side, the right-hand side doesn't have any occurrences of that thing, and a couple other rules. But basically, the things that are needed in order to argue that you could just replace the left-hand side with the right-hand side everywhere, and then it would still be a proof. This is the classic, if you look in the textbooks, this is why people say making definitions is okay, is because they're conservative in the sense. So if you have that check, then great. But again, this is an external check. This is not something that's part of the MetaMath kernel itself. So it would be nice to have a system that also allows you to have definitions. And so, okay, so what does it take to have MetaMath plus definitions plus trees? Like if you have your expressions be tree structures, well, you don't really lose anything in terms of the structure of how MetaMath checks things. But one of the things you gain is that it doesn't matter even if you have an ambiguous grammar. Like it'll impact your ability to write things. Like you might write something and it might not mean what you think it means, but it's not like the system's going to simultaneously think it has two different parses, be able to derive weird things from that. So you only get sort of pretty printer issues if you have weird grammars, whereas in MetaMath you get actual unsoundness. So that's sort of the starting point for Metamath Zero. It's basically, okay, let's take MetaMath, add definitions, and then use trees, and then change the keywords that they aren't $C and whatever. They're just words.
That's good. Well, I mean, it helps.
give it a little bit of a modern vibe.
Right, yeah.
You gotta do that in order to sell it, right? So so it doesn't use obnoxiously inexplicable names. But I mean, other than that, that's really all that there is to Metamath Zero, the language.
Yeah.
So the core language is really only doing that. And then all of the rest of the project is like building stuff on top of that base, right? Or building tooling to work with it and things like this. One of the first things that I did was I wrote a translator from MetaMath to Metamath Zero. This was an early approach to just make sure that, it still is useful and it works. And it's, you could just read a MetaMath file and produce put in the operators in the same structure. And so that gives you same theory, but now written in MM0 syntax. And then you run it through the MM0 checker. And one of the things that I'm happy about is that doing this, I was able to produce a Metamath Zero file and then check it. And that takes, checking the original set.mm in MM0 syntax takes 0.2 seconds.
Oh, wow.
So I can beat the state of the art for checking MetaMath by just translating it into this new format. So basically that sort of validates that, okay, we can actually, we can double down on the things that make MetaMath good for these aspects, right? And this basically amounts to like, okay, encoding the proofs. So I guess one of the other things that I didn't mention is that in MetaMath, the proofs are these sort of encoded blobs after the proofs. So you'll have like $P statement, $equals, and then a bunch of capital letters in a sequence that looks just like there's just this solid block of letters.
That's the proof.
That's the proof. And it's written in this sort of encoded style.
Right,
I mean,
right.
It's possible to figure out what it's saying, but it's really intended for machines.
Right.
And that's because writing it out, you could write it out as like an S expression or something like that. But this is a more compact form for the thing. But putting those two in the same file, I think, is not great for humans. You've got like the comment that says what the theorem's about. You've got the statement of the theorem. Those two are kind of written in this human readable style. And then you've got the block of text, which is like, okay, just please ignore me kind of thing. And I mean, you can see that stuff if you run it through the HTML. So there's using the tool, you can produce the HTML web page, which you can also see online. And that's the version of the thing that people are actually supposed to look at.
With the actual table, with the references, and where it's your proof state looks like.
Exactly.
Right.
So that's the sort of, that's the for humans version of the proof.
Right.
But yeah, having both of those two in the same file, I think is really serving two masters.
Right.
And so in Metamath Zero, those are two separate things. There's one file which is the theorem statements, and then there's a file which is like a proof file, and this is just a binary file format which is, optimized for being able to check all of the things in it.
I see. So then the way that you prove the theorems is going through something similar to like the cocktop, and then that will be produced in the binaries.
Yeah, so actually, that's an interesting question, and it leads to the sort of next part of this project, which is Metamath 1. So Metamath 1 is the proof assistant for Metamath Zero.
Okay. I see where this is going.
So the idea is that Metamath 1 files have basically the exact same syntax as Metamath 0, except Metamath 0 doesn't have proofs after the theorem. So you say theorem, statement, and then semicolon to end the thing, and then that's that. And what Metamath 0 files are really specifications of like goals to prove, right? Like with the example I gave before, if I would write down theorem, Fermat's last theorem, the statement of the thing, and then semicolon, and then I give you a file which says, starting point is, I don't know, ZFC or piano arithmetic or something like that. Ending point is Fermat's last theorem, and then that's the file. And then I want to have a theorem, the meta theorem here about the proof assistant is that if I have this file, then there's no way for the proof for the checker to say yes if I give it this file and also an arbitrary binary blob of stuff, unless that theorem is provable. So that's the statement, right? So the idea is that the binary blob is all of the untrusted stuff. And then the Metamath 0 file, that's why it's a human readable file. It's so that you can read the statements of the theorem. So it's important that the statements of the theorems be at least somewhat read. So you need to have like notations and things like that, because it's important to be able to present the statements of your theorems, because otherwise it can sort of fool you, with like, I don't want a thing that will check my binary blob alone and then say yes. And then you'll be like, okay, that's a well-formed, does it prove my theorem? I don't know. Maybe like you basically, there's two options. Either you have it tell you when it's done what theorem it proved, and then it has to figure out how to pretty print those things. Or you can give it the theorem in a human readable format, and then it parses it. So it's like I can choose to either have a verified pretty printer or a trusted pretty printer or a trusted parser, right? And so the parser approach gives you the ability to structure the thing in a way that looks as nice as possible. And so that's sort of the approach that I took with this. But yeah, so the idea is that this binary thing is really just the untrusted stuff. So it actually has more, it can have more theorems in it, more definitions. This is, you're allowed to introduce more things, but you can't add more axioms. So this is how I can have this property that like, I give you the axioms and then you can do whatever you want, throw ChatGPT at it, random things. At the end of it, you have to give me something that runs through this checker, right? And I want to know that if you can do that, then actually the theorem does follow and you weren't able to break my system through some, nefarious means. There's no obj magic. There's no, there's none of these, little soundness holes, which like, it's fine for practical purposes. No one's probably going to go there. If you talk to different people in the different systems, most of them have some kind of out, and then they have to have an argument of the form like, well, we're not assuming that our users, like the people who are producing the proofs, are like actively malicious, right? Where, we're not going to make any claim really of that form. But then that means that if you do receive some proof of something, if you ask the question, okay, what do I have to look at in order to understand? The answer becomes, well, you have to read the whole proof, make sure that nothing weird is going on, make sure that they aren't writing any tactics that redefine theorem to looks okay, bro. There's lots of these techniques that exist in these systems, which people sort of just close their minds to it because it's difficult to deal with. I'm trying to see if we just start from the ground up, like what could we end up with for a system which tries to actually tackle this problem?
Okay, so the main idea here, let's see if I got this right. So it has to be something so small that it's actually hard to have something wrong.
Yeah.
Right? And then now, not sure if you thought about this yet, but then to have this notion of correctness or of soundness of you're doing what you're supposed to be doing and nothing else is a very simple, straightforward reasoning that is easy to follow. And is that formalized within itself?
Yeah. So the reason why I'm talking about these sort of uber adversarial approaches is because I want to prove a theorem. And a mathematical theorem is in some sense the worst adversary possible, right? If I want to actually prove a theorem that says there is no way for you to break it, there has to actually be no way for you to break it. There can't, be these things that we sort of ignore. Right. They will just make the theorem not possible to prove. So I can't have that kind of thing. And then also, the effort that goes into writing these proofs, it gets a lot worse if the system is complicated. And so that's why I want the system to be absolutely as simple as I can possibly make it so that I don't have as much proof work. It's like it has to be correct for obvious reasons. And then that way there's, some hope of being able to prove the correctness of the kernel itself. And so the original goal of the project was, can we construct this theorem prover and then prove its implementation correctness? And when I talk about implementation correctness, what I mean is that this property of I have a binary. That binary is encoded as bytes on some architecture, let's say x86. And then that program is handed, two files. It's handed the file of stuff that we want to check, and then the file of untrusted proof stuff. And then if it says yes, exit code 0, success, then theorem follows from axiom. So there's some definition of what it means to interpret that file within the language. So you have to specify what's the language itself, all the stuff I just told you, and then what does it mean for theorem to follow from axioms? This is some kind of syntactic thing about putting stuff together. And then that property, whatever it is, that holds for the file if the checker says yes. Mm-hmm. And so that whole statement, that is now, the goal of the project is to have a proof of that theorem. And I have to say that the project isn't done. So there are still some components of this that have to be done. And in particular, it's sort of at the stage of building out this verified compiler and getting it to produce theorems of a variety of facts. In particular, one of the facts that I wanted to give me is this one about having a program that checks these properties. But in general, because I ended up having to write a compiler, that compiler can generate theorems of all kinds. Then there's still the task of writing the verifier itself in that language and proving that's correct. So yeah, there's sort of many stages to this sort of design, but I think it's going well.
How does this approach of proving correctness compare with, say, Metacoq?
So one of the differences, so Metacoq is a statement of the logic of Coq and a kernel for it written inside Coq. So this differs in the sense that it's not going down to the same level. It's actually constructing an executable function within Coq's logic, which is some steps removed from like an actual running executable. There's actually a pretty large gap between Coq and, x86. Mm-hmm. There's like the Coq kernel which is implemented as a bunch of ML code. And then there's the ML or OCaml compiler. So you would need to know what that compiler is doing in order to turn that into actual executable semantics. I referenced CakeML earlier. CakeML is a project that's been developed by, it started with Ramana Kumar, and Magnus Myrene here in Chalmers is doing CakeML stuff. And this was one of the reasons why I wanted to come here to Chalmers, was to work on CakeML, because it's also sort of addressing many of the same issues that I think about every day. In particular, CakeML is a verified ML compiler. So CakeML is able to read a variant on ML syntax and produce programs. And the CakeML compiler, as a sequence of bytes on x86, has actually been verified to perform that compilation task. And so it's like, that is, I think that's where we should be as a society, but it's just such a long road getting us to the point where this is more normal. Right now, there's only a few exceptional projects that are doing this kind of thing. And I think that building on top of verified ITPs is something that I would like to be the future. Like, I want the future to consist of a bunch of unverified ITPs that are translating their stuff to ITPs that have been verified. This situation already exists for SAT solvers. SAT solvers, these decide propositional logic, which is much simpler than the full stuff that most ITPs do. But SAT solvers can still be quite complex, and people use them to solve all sorts of complicated tasks. But SAT solvers can generate proofs in a format called DRAT, which in particular, because at the SAT competitions, they started saying you can't enroll in the competition unless you can produce proofs. So this really got people to to change their ways and actually start producing proper proofs. Mm-hmm. But okay, so now the SAT solvers are all producing proofs in this DRAT format, and then people wrote proof checkers for DRAT. Gotcha. So. Yeah. And then they wrote proof checkers in, so like, you can translate DRAT into an even lower level format called LRAT. And Youngkyum Tan wrote a checker in CakeML for checking LRAT proofs. And then proving the correctness of that. So now you have a really high assurance checker for the proofs that are generated from your SAT solver of your choice, right? And so now we have a full, complete pipeline, right, from, we're generating reasonable proofs and we're able to check them practically using some, high performance tool. I want to see that for ITPs too. Mm-hmm. And it's annoying that it's taken us so long to get to this point, but we're finally starting to get there. But a huge part of that is just understanding how every system represents its material, so that we can translate it into a system that has some self-verification or something along these lines.
I love that idea. It reminds me of watching Frick's Widgets talk. He goes really deep into having this notion where you have your kernel, you have your proof assistant, you can do all sorts of crazy bad shit in there, but then you should have an external verifier, an external type checker maybe. So I remember seeing that there's another Coq project that is a re-implementation of the type checker that I think they stopped, like they didn't get all the way, and it would be a similar idea, right? But so the whole point is that, well, whatever, just do whatever with your proofs and your type system and whatever, like produce some, but then give me the witness and let me check if that witness satisfies the original property with the rules that you were saying that they satisfy, right? And then so that's the deeper raison d'être, the reason of being of Metamath Zero.
Yeah, exactly.
So I am obliged to ask the next question, which is, how does it compare with Deducti?
Mm-hmm. Yeah. So for those who don't know, Deducti is like also a system that basically fits itself in this interchange space. Like Metamath Zero is a language which you could translate your logic to. And Deducti is also a language which you can use to translate your language to. So, and I mean, Deducti is, to be perfectly honest, like it is much further along in solving this task. You know, they have money and they have people,
and, professors and students and the whole shebang.
Yeah. So, in particular, you know, so they've got a bunch of translations, and they are much further along in this task of like linking up a web of different proof assistants together into one thing. So in order to make use of that, well, you need to translate it into some common language, and that language in Deducti is called LambdaPy. LambdaPy is, you have Lambda and you have Pi and you have rewriting. So the idea is that you can represent terms using kind of dependent type theory, but you can also give equalities as sort of rewrite rules. And this is how type checking proceeds, is that like when there's a mismatch in types, then it attempts to use the rewriting rules to make them the same. And then if they are, then it type checks. So this foundation is somewhat more complicated than what Metamath Zero is doing. So Metamath Zero is sort of based on Metamath's general approach to things, and so there's really no rewriting. There's just syntactic matching of terms. One of the advantages of this is that you actually get good bounds on how long it's going to take to run things. So like when you substitute a theorem, you have to give it all of the substitutions, and like in the proof term that's given to Metamath Zero, there's all of the substitutions to apply to which theorem, and so it's all very explicit. So you have to perform a substitution into each statement, and that can be done in like linear time. And then you do equality checking for subtrees, and that can be done in constant time because everything is sort of pervasively deduplicated. And so these proof terms are all sort of DAG-like in structure, and you never have to check the same thing twice. And so there's basically a bunch of algorithmic optimizations that are done in order to ensure that it doesn't hit some like exponential worst cases. And because of that, you can essentially say that, well, the checking time of a Metamath Zero proof is its linear time if you assume that the sizes of statements are bounded, and its worst case quadratic time, although that worst case only occurs if you have one theorem that takes up half of the proof. And then you spend the rest of the proof applying it many times. It's a very difficult edge case to get to. So it's reasonable to have this assumption of roughly constant compared to the size. Like the size of a library is generally going to be much larger than the size of any individual term.
Right.
So that's the sense in which it's basically linear. And if you compare that to the check time of if you're doing rewriting, well, it's actually difficult to put a bound on that because you don't know how much rewriting. The check time of like dependent type theory, like Calc and Lean and these sort of things, is actually the fastest growing function I know. Like you can win largest number competitions by using this function. Because they do terminate, but the bounds are just astronomical. So yeah, with linear time checking, it means that you basically get this property of being fast, both in theory and in practice. And with rewriting, you basically don't know in advance. I mean, I say that like type checking is slow in theory for dependent type theory, but it's usually not slow in practice in the sense that people usually don't write those things in particular because if they take too long, they give up and try a different proof strategy, right? So it's a sort of gamble on my part to say that I believe that if you were to translate these proofs into a system like Metamath Zero, where all of the rewriting steps are explicit, that the proof size doesn't explode because the check time, so basically the size of the proofs is going to be bounded by the check time in the original system. And so if there are ways of making it fast to check, then we can encode that with proof rules. And so that's sort of how all of the translations work, is they're implementing the rules in a way which ensures this asymptotic order doesn't grow. So like it doesn't get worse by more than a constant factor. And in many cases, we can do a lot better, in particular because we're not searching for the proofs. We sort of have the proofs and then we're just checking them.
Okay, so both of them, okay, now we have this minimum logic language where things run extremely fast, it's easy to verify, and we have this minimum working language that, so we have Metamath Zero and we have deducti, where it's one of the ideas is to have them to be the target for being this checker of these languages. Another thing then that I wonder is the notion of, it's not exactly straight, because okay, so now that you have this extraction mechanism, okay, you have all your theorem provers and you do not care anymore if they're true correct or how fast they go, as long as you can extract those proofs through this minimum core, let's say Metamath Zero, and then you trust Metamath Zero because of all the properties that you just explained. So now there is another gap here that must be filled, which is comparing the two semantics and showing that this translation preserves some sense of this semantics. Can you comment a little bit on that?
Yeah, so one of the aspects here is that the translation itself sort of expresses the semantics. This is actually one of my secret reasons for wanting to have exports from systems, is that if I pick some other system that I don't understand, one of the ways that I can come to understand it is by writing an exporter for it. Because in the process of writing an exporter, I have to grapple with all of the things that the kernel does, and in particular, why people seem to have a belief that what it's doing makes any sense at all, right? So I have to understand where all of that is going in order to produce proofs in my minimal language that, of course, doesn't have any of the features that exist in that other language, whatever they are. So the translation has to be it's sort of trivially semantics preserving to the extent that it works at all. It's defining its own like in the target, we're going to define the semantics. We're going to write down in Metamath Zero, we're going to write down like the rules of Isabelle or something like that. And then we're going to translate it. And then if it works, then it was able to make some sense of something there. It could end up that, well, okay, so your translator, maybe, let's say that the translator just translates everything to true, right? Yeah. That would not be, that would not be great. There's sort of the backup approach of like the reason why, as I mentioned before, the reason why there's two files with Metamath Zero is one of them is for you're supposed to read it and know what's being proved, right? And so when it comes to exports, the idea is that, well, you're trying to export something. You have some final theorem. Let's say, you heard that someone proved the prime number theorem in Isabelle, and then you want the prime number theorem in Lean, and so you want to use some tool, you press a button, and then poof, all of the stuff comes from Isabelle to Lean, and then you can use that theorem. Well, if it turns true, then you wouldn't be using that theorem, right? So there is another task here when it comes to extracting theorems from one system to another, which is a thing called alignment. The idea is that, Isabelle has natural numbers and Lean has natural numbers, and 100% guarantee that after this translation, the Isabelle natural numbers are not going to just magically happen to be the same as the Lean natural numbers. You have to have some place where you insert, like, okay, if you see the encoded Isabelle natural numbers, translate them to the Lean natural numbers instead of what you would have done otherwise. And now you have additional proof obligations with regard to how that relates to all of the other translations it's going to do later. But you can do this sort of thing. In fact, this was one of my early tests with the Metamath Zero translations. Was I had a translation from Metamath to Metamath Zero, as I mentioned, and then I also created one from Metamath Zero to Lean. And I used this to translate the entirety of set.mm into Lean.
Okay.
I produced a bunch of Lean files with all the stuff.
So you actually split the files this time. Not one single huge one.
I cut it up into several files.
Good.
Lean had difficulty processing extremely large files. For some reason, not everyone does this. I don't understand. So yes, I broke it up into a few pieces, but it still checked. In fact, it checked surprisingly fast. Like it was, I mean, even though it's now using Lean syntax, like I generated Lean source files, right? And so Lean has to do a bunch of elaboration and stuff, even though I've put @ signs everywhere and made everything explicit. And so there's really nothing that Lean really needs to do, but it does it anyway, whatever. And so processing those files took, I don't know, like a minute or something like that.
Wow, nice.
So not as fast as, the Metamath original proof, but still, way faster than Mathlib, right? And then you end up with a bunch of encoded state. So this was translating all of the Metamath axioms into Lean proofs about a model of ZFC inside Lean. So Lean is actually stronger than ZFC. It has some inaccessible cardinals in it. And so you can actually construct a type, which is a ZFC universe. Within that, you can prove all of the theorems of ZFC, and then we just map all of the axioms to those theorems. And now you get a proof just from Lean's axioms that, some high-level theorem in the set dynamic. So like I tried this with the prime number theorem and with Dirichlet's theorem. And so these are, early proofs that I did, which are high-level mathematical results, which you can now get them in Lean as, and you just had to align a couple concepts, right? You align like the natural numbers and prime numbers and infinitude and, whatever it is to state Dirichlet's theorem. All of the other stuff, Metamath defines tons of other things. We don't have to align those. We only align the things that are in the statement. So it was actually not that much work to get one of these FFI-based theorems, and
then once you did this little alignment, and then you ran your port, then it was done. You didn't have to fix anything. It was
100%. It just
amazing.
Goes
that's
right
awesome.
through.
Yeah, right. That's a dream.
Yeah. That's and this is one of the things that I like about Metamath. Again, it's like it's easy to do this kind of thing because there are so few concepts in Metamath. It's like there's nothing. There's only a couple things that you have to handle, and then you're done with the processor. And most of these other languages, it's a lot of work to understand all of the concepts that go into the kernel.
And I assume that you were like in the Lean side, you were actually generating the term, not the tactics.
Yes. Yeah.
Of course. So it's just a readable blob of.
Right. So like in Metamath, there aren't really so Metamath has a different approach to tactics, and actually, maybe I should say something about it because I think a lot of people get this confused. It's not that Metamath doesn't have tactics, although sometimes people will say that. When you open up set.mm, you will see all of these encoded proof terms. There will not be a tactic in sight. None of the Metamath verifiers know about tactics, and they're processing this file that doesn't have any tactics in it. However, there are proof assistants for Metamath, and those proof assistants do have tactics. But the thing is that those tactics are used to produce proof terms that then end up in the library. So the thing that gets committed to, GitHub is just the proof term and not the tactic that produced it. So this is, it's a different approach to doing this sort of design. And it is absolutely one of the most important things for why it takes so little time to check, right? Like, and there are legitimate reasons to say, okay, I'm not sure we want to do this. Like we wanted those tactics. If it breaks, then we want to be able to fix it, or like, not have to change anything. Maybe if I have a very automated proof, then it's more able to cope with changes to the library. There are definitely arguments for why you would want to keep the proofs around. But I do think that caching proof terms, at least, is very effective as a way of reducing check time by orders of magnitude, and not rerunning all of the tactics all of the time. That's effectively what Lean and Isabelle and these other systems are doing, is they're just running all of these tactics, and they have to do so because it's part of the source code. That is the source code. So you have to anytime anyone changes anything, then you have to rerun all this stuff. Whereas if you just committed the proof terms, then it's all fast.
Yeah, it's fast, but it's less maintainable on the other side. So it's a bit of a trade-off.
Yeah.
These are very, very nice, interesting projects. One thing that I would personally like to do, and it's something that I might continue my academic career into, is to try to figure out a good system, a good way to compare these languages, right? To show the strength of different languages and have almost a technique, an algorithm, a method through which you start doing this translation, these ports, like what are the properties that we're looking into, not only languages, but proof systems, which are languages on steroids, right? But what should you keep in mind? What are the semantics that you're comparing? How these semantics compare? What are the axioms and also those axioms that are compatible or not? And that's also another issue that you have in these ports too. Sometimes Coq libraries are not compatible with one another because of assumed axioms. Now imagine even exporting to different proof systems. Now we're talking about a complete havoc, right?
Yeah. I mean, one of the things that you get as a result of an export is the ability to put. I mean, that's what you've done, is that you've put everything into a common language. So now they're speaking the same vocabulary, right, and you can see how they relate. You can align them if they don't relate exactly in the way you want. You can do sort of total translations like this Metamath one that I described. But you can also do partial translations. You can say, I'll translate Coq into whole light, despite the fact that Coq is, more powerful in terms of its axiom system, right? Mm-hmm. There are theorems that, like, Coq can prove the consistency of a model of Hull, right? So clearly not all Coq theorems are going to be whole light theorem. Yeah.
I don't know that. That's very interesting.
So high order logic fits within the cumulative hierarchy up to level 2 omega.
Right.
So it's relatively it's weaker than VFC, and it basically is because, well, you don't have dependent types, right, and you don't have. So the most you can do, you have one infinite type, and then you have the ability to create function types. So you can make bigger and bigger and bigger things, but only finitely many times can you apply the arrow constructor. Mm-hmm. So that's why everything sort of stays at this level, above the infinite, but below the twice infinite. So, whereas with Coq, you have a universe, which is a type. And so, like, the universe itself contains all of this stuff. Mm-hmm. And then we're saying it's a type, so now it's got all more stuff. Yes. You can build even more stuff on top of it.
Ad eternum.
Yeah. Yep. So that's why you end up with a much stronger axiomatic strength for a system like Coq.
See, these are the things that I'm saying, that you have to do this. You have to have this, keep these things in mind. And it's another issue that we've been discussing this today and yesterday, is those things are not well documented. Like, these are folklore that you only learn once you're doing a PhD, because your PhD advisor learned with his PhD advisor, learned with his PhD advisor, all the way to Tarski or Alonzo Church or whatever. And it's tricky, right? So
yeah, and I mean, I think I'm not even sure the consistency strength of all of the major proof assistants. Like, I believe that the consistency strength of Agda is either 2 omega Malo cardinals, which is an extremely large consistency strength.
Say that again, 2 omega.
2 omega Malo cardinals.
I don't even know what that last part means. Okay.
A Malo cardinal is like an inaccessible is inaccessible. It's even more.
Okay. So you don't know if Agda's.
So it's either that, or it's a subsystem of second order arithmetic.
Which sounds reasonable.
That's contained in the power set of the natural numbers, right? It's just like vastly different levels of the consistency strength. This has to do with predicativity and the role of predicativity in, like, being able to construct these weird non-classical models that exist at very low levels of the hierarchy. The one that uses the Malo cardinals is where you're using, like, sets or types, kind of the sort of classic style of doing this thing, which is sort of very strong. It validates impredicative action. This is why you have to use this for Lean and for Coq, because they have impredicativity. But yeah, so I'm asking around, here, there's a bunch of Agda heads, and I want to understand how does Agda, why do we believe Agda is doing something reasonable? That's sort of the starting point for creating an export, is we have to know what the model is, right?
Okay.
And we have to understand, why is it consistent? Okay. And the answer is really complicated in Agda, because in many situations, the answer is, well, it's not. We have a bunch of compiler flags, and you can turn some of them on.
Yep.
And we know that some unspecified subset of them are inconsistent with some other unspecified subset. So formalizing Agda is like formalizing, 2 to the 100 different systems based on all of these different flags, settings.
But it's kind of the purpose of Agda too, is to be kind of like a playground. And
Exactly. It's a type theory playground, which means that you want to have those mechanisms, but you also want to understand those mechanisms. And I think that, there's some important unfinished work when it comes to sort of the other side of a proof of system. You can't just add axioms and then go on with your life and, prove things and think that those things mean something. You have to also validate that those axioms are true or correct, or have some relative consistency result with respect to something else that, is more understood, right? If you're just inventing it's one thing to be inventing a type theory. It's another thing to be inventing an implementation of a type theory and hoping that it has some relationship to the type theory that you wrote on paper. So yeah, this is sort of why I'm very interested in sort of exporting the systems, is because I want to understand, how does all of this work? Like, why are these things doing anything reasonable?
And then in order to do that, you're just now learning all kinds of different interactive theorem provers to really have a grasp of all of them as much as possible.
Exactly. So I've been looking into essentially every single one of the major interactive theorem provers.
Let's list them real quick.
So obviously Metamath, Lean. So I wrote a Mizar implementation last year. Isabel, Whole Light, Whole 4 now. I am hoping to get Agda on the list soon.
So you don't do much Agda.
I don't have Agda.
For me.
Yeah. So Agda's on the to-do list.
Lean, we didn't mention.
And Cock,
I feel we might have forgot something.
Maybe we counted one twice or something.
And what's your favorite?
Oh, what's my favorite? Well, okay, for day-to-day, like, theorem proving work, in absence of any other constraints, I would probably use Lean. I think the Lean is the language that I have the most personal familiarity with. I think they're all very good systems. And I don't know, I think that to a great extent, we don't pay enough attention to the systems that aren't, our home base.
Yep.
We need to, branch out a little and know that people have solved the problem that you're looking at now already in another system. And it's not just, there's mathematical theorems. Some people have proved this or that in another system, and it would be great if we could share that kind of knowledge, but also implementation work, right? Like, people have implemented versions of type classes in almost every system. Like, it's a very, it's a convergent evolution kind of thing. Yep. Even though they've been implemented in completely different ways, and those differences have their own downsides, each one tries a slightly different version of the technique and then runs into different issues because of that. But still, it allows us to understand sort of the trade-offs of these design decisions.
Okay, so we were talking of how you wanted to learn as much as possible so that you understand the differences and the comparisons, right?
And also because I want all of these systems to be within this umbrella that I'm talking about, of like, we've got all of them being translated into some system that we have high assurance because it's got some self-verification style proof or some mutual self-verification. So like, talking again about the differences between like deductive versus Metamath Zero versus open theory, which is a translation between the different whole proof assistants, or other interchange languages. I think that it's not that we need to have one thing at the center. I think it's more like a web. We have a bunch of different systems, and they can all translate, because see, the thing is, all of these systems, they're all math complete. right? They're all able to represent math more or less. And that's the thing that we want to translate. We want to translate the practical mathematics from one system to another. And then even though these all have slight variations on what's provable and what's not, most of those things just don't matter in practice. Like whether you have mallow cardinals or inaccessible cardinals is not something that the average user of the system is thinking about. And it's not something that's going to be reflected in their proof in almost all cases. So if we can translate these different systems, these proofs across different systems, well, one of the things that we can translate is these self-verification proofs, right? If I have a proof that Metamath Zero that a Metamath Zero implementation is correct in one, or is implementation correct in Metamath Zero, well, I can press a button and get that proof in Lean, right?
Yes.
Now I have a Lean proof that Metamath Zero is consistent. And now if you have, maybe you don't trust this weird new Metamath Zero system, but if you do trust Lean, then, these translations give you ways of saying, okay, yeah, now I have it in a system that I understand better. And within the system, I am now getting this fact. So like, if we can have proof of correctness of these various systems, then we can translate them, I don't know, pick your favorite system, and then we'll translate it there. And now you'll understand, we can move everything into your home system, whatever that is.
That's pretty cool. So to wrap things up, we've been here for a while. The end should already be around 2 hours of the episode at this point. So I need to ask, because there's been some very interesting discussions in the past in the internet, and I must confess that this is one of I put in a favorite tab so that I open it sometimes that I need some amusement on my side. But there are some people in the community that let's say there are some people in the community that is quite skeptical about the consistency, the strength of Lean, because it breaks some particular properties that type theorists holds very dearly in their hearts. I'm not entirely sure. I think we talked about a little bit about this yesterday at the first half of the episode. But I think something related to normalization, something related with
transitivity and subject reduction.
Right.
And strong normalization and canonicity, I think, are the ones that are you're gonna.
Exactly. Thank you. So yeah, you're gonna get into those details, but just to wrap the core of my question here is, I think you are the right expert to comment on why, in the end of the day, this doesn't matter as much, and why you're confident that Lean will succeed despite this inconsistencies.
Well, okay, so I mean, regarding will Lean succeed despite those inconsistencies, I think that for the most part, mathematicians don't care about this kind of thing. Like in a very literal sense, like this is a foundation. These are foundational questions, and foundational questions are not something that keep mathematicians up at night. Like
that's the truth. We may hate it, right, as type theorists, but that's the truth.
It's
whatever.
You got to get used to this fact that, like, okay, is it helping mathematicians in practice communicate their results to others, right? Communication, I think, is much closer to the core of what mathematicians want from these systems. And I mean, historically, communication has been one of the areas where interactive theorem provers struggle the most. Being able to express your results in a way that other people can understand is actually really important to mathematicians. And when writing in the system means that gets turned into unreadable garbage, and then I show it to a practicing mathematician, and they're like, "What is this?" Right. It doesn't read. It
doesn't give you any insight about what is actually going on here. Exactly. So why should I care about this?
Exactly. So so this is why these first impression, like the one that you described, you look at MetaMath, on the website, and then you see all the crazy stuff, and you're just like, what is this?
Whatever.
This does not, spark joy. This is not something.
Right.
This is not something that makes you want to use the system or interact with people that do use the system.
Quackheads. Weirdo.
Exactly. So I think think that those are actually extremely important for adoption. Like, if you want these systems to actually be used, you have to make it look good. Like, that, it's embarrassing to say this sometimes, but like marketing and like, presentation and usability, user experience, these things are actually extremely important if you're thinking about actual adoption of the language. And you can't just, have good type theoretic properties and ignore the rest of it and get a system that people are going to use. So that's one thing. Like, just being able to solve that is I think much more important than the type theoretic properties. But like, okay, why don't the type theoretic, like, if the system was inconsistent, I think that the discussion is a little bit different. So I do think that mathematicians care that the system is not inconsistent, although they don't necessarily, like, it's not something that they're going to be watching actively. It's more some property of the society around the ecosystem of the proof assistant should be addressing soundness bugs within reasonable order. It doesn't mean that you have no soundness bugs, but like, there should be some evidence that as a culture you care about not having them. But like, as far as having a proof of soundness, well, some people care. I will care, obviously, but not everyone is like me. I think that as long as it, covers the things that look like mathematics, that's probably going to be where most mathematicians are like, yep, that satisfies my concerns, and now I'm going to move on to the things that actually interest me, like modeling schemes and differential topology and all of these other things, and then not thinking about the foundational stuff at all. In fact, if you talk about, strong normalization and canonicity and subject reduction, most mathematicians are just going to be like, what?
What the fuck?
What are you talking about? I've never even heard of these concepts.
Yep.
It's not clear why I would care about them. It's something which a type theorist is going to care about. Yes. And it is in particular something that makes, we talked a little bit about Lean4Lean yesterday. Not having subject reduction and transitivity of definitional quality and all these things, these are things that make my job harder, right? These are things that make it much harder for me to prove that the system is actually sound, right? Because it means that there are certain techniques that you just can't use. Like, there are a lot of techniques for proving soundness which involve like constructing a model where the proof is actually going to prove strong normalization at the end of it. And so it's like, okay, I clearly can't use that because I know that strong normalization fails to hold. So if I attempted to use this result, then it's not going to apply. So I have to find some other way around, right? I have to come up with something new, which is going to establish just soundness and not give me all the type theoretic properties that I already know to be false. So yeah, it's annoying, as with my type theory hat on. It's something that I wish were different, but maybe not that I wish were different enough to, poke the developers or, try to change the world on this one. This is something which I think I can work around, but yeah, it's less than ideal from a type theory standpoint.
I think I really like this perspective. I think it really rings a bell here. When you talk about, like thinking, you already start the answer here thinking about the user, about the mathematicians, which is a very important use case of why we do what we do. And I think there's a clear difference here between, like, for example, we're talking about Agda. The reason why Agda exists is just so we can play around with type theory and implement these things. I use just with a lot of quotes here, but like that's the main idea of what's going on here. But if you really want to develop a interactive theorem prover that will be widely adopted and successful, we must have the end user in mind, and have the not only the end user, the user experience and the tooling around it, and it's going to be doing reflecting how the user wanna use these tools too, right? And I think that's something that Lean that makes Lean to be so successful.
Yeah, and it's nice that you bring that up. Like, Agda has a user base. Their user base are type theorists, right?
Yes, precisely.
If you want to make a system that is good for type theorists, then you want to have a million flags that you can turn on and off so that you can have exactly the type theory of your dreams, right?
Yes.
And then you can play with the consequences of that system. And soundness, or like consistency, is actually not at the top of that list, right? It's not the important thing. What matters is, does it, am I able to express my thoughts within this language, checking, I want the checker to make sure that it's following the language that I'm specifying, but like whether the system as a whole is consistent, that's not, like one of the side effects of like insisting on consistency is that you're probably going to be very resistant to accept extensions to the system, right? You don't want to just add a million extensions because one of them could interact with the other one in a weird way and prove false. So if you want, it's sort of a mutual exclusion here. You can't have both, consistency all the time and also a million extensions of unclear, interaction potential. But it's serving its users.
Yep, serve the users. I think that is the perfect note to end this episode on. And this was an incredibly pleasant conversation. I'm really happy that we got the chance to do this in person. And is there any final remarks, any closing that you would like to bring up?
Metamath Zero is open for contributions.
There you go.
Yeah.
Perfect. So it's on GitHub. Everything's open source. Anyone can come in. Is there anything in particular you would like to see? What kinds of contributions you would be looking forward to?
Yeah, so I'm currently like neck deep in some compiler correctness proof, and being able to develop that compiler to be more practical and making sure that it's usable for more use cases and this sort of thing would be incredibly useful. And making the proof assistant closer to a real, it has some VS Code mode where you can like hover over things, and
that doesn't exist yet.
It does exist.
Nice.
But it could be better.
Yeah, of course.
So making it practical and making more translations into these different, if you are able to, if you use another proof assistant, think about how we can get exports from the system, and keeping the exports alive is, I think, one of the biggest issues that is faced with all of the export systems. There have been many exports that they're built, someone writes a paper, and then the systems move on. And these things aren't checked in. They're just, their own separate projects. And so they age and bit rot. And, this is a very frustrating situation for anyone who's trying to keep this sort of web alive, right?
Yeah, for sure.
So yeah, if we can get more, interaction between the system developers and the export developers, that would be super useful.
Awesome. Well, so make sure to check the links in the episodes. You can find the Metamath Zero link over there and bring on your contributions. Thank you so much for this conversation, Mario.
Thank you too.
That's really funny, man. I don't know if you could notice from this interview, but it was really impromptu. We didn't prepare much, but Mario is just such an incredible person, extremely smart, that we just went through with it. Just was literally just hanging out and talking with each other. And it's really funny because I was visiting Chalmers, and I had no idea he would be there. I randomly figured out he was just started his postdoc the week before I visited, so he was just there hanging out. He just started, and like when you're setting up, you don't have many friends or anything like that, so he was just sitting in his room doing his work, a lot of work. I mean, he works a lot. But so I just shoot him an email, hey, let's grab coffee. And in the middle of the coffee, I was like, hey, let's record an episode. This conversation is going really well. Let's just record whatever we come up with. And we just start talking about all his projects and make things a little bit more formal. But overall, it was just a random conversation. Oh, man, it was so cool. It was so great. It was an incredible experience to meet him in person. And then things got even more fun because the week I think 2 weeks after that, we were both in France at the same time. So I just sent an email to the Coke developers and asked if I could hang out in Nantes. So that's foreshadowing of what's happening in the next episode. I'm going to be talking directly with one of the main Coke maintainers, Pierre-Marie Prédot. And that is one of my favorite episodes so far. I mean, I love all of them. This conversation with Mario was great as well, but Pierre-Marie was a whole other level. He is incredible, and I'm really looking forward to finish editing the next episode. It will come out very soon after this episode, so stay tuned. Follow our Twitter, TT4All, and send us an email if you're interested. Don't forget to join Discord, that whole thing you guys are very tired to know about. So I'll see you guys next time.
Este podcast foi editado por Play Áudios.